This session is code analysis. We learn how to write a code to set up interrupts in TM4C123. The lab corresponding to this lesson is to make an embedded system that whenever the button is pressed, not held, just pressed, the counter's number increments by 1. The system displays this number on a LCD. We need two files to make interrupt working. Startup.s and the main.c. Later, when we design this embedded system in the lab, we need more files. They are the systic.h, systic.c, the LCD driver, lcd.h, and the lcd.c, and the pll.c. Do not worry about these files for now. Let's discuss the register used for this design. We need 8 registers. Yes, 8. A lot. We need these registers to make interrupt work. We go over them one by one. The first register is the GPIO PCTL register. The detailed information about this register is on page 688 of the TM4C datasheet. The datasheet states that GPIO PCTL register is used to select specific peripheral signal for each GPIO pin. The wording is pretty confusing. It just means certain pin of a port is protected. In order to use them as GPIO pins, we need to unlock them. If you are interested in which pins need to be unlocked, check the table in datasheet on page 688. This figure is the register map of GPIO PCTL register. TM4C123 block is the first nibble. In case you forgot the meaning of nibble, here is the definition. A nibble is a group of 4 bits. For the first nibble of this register, TM4C123, it is bit 0 through bit 3. These 4 bits together used to unlock pin 0. The second nibble, bit 4 through bit 7 are for GPIO pin 1. To unlock a pin, the corresponding 4 pins need to be filled with 1s. That means every bit of the nibble need to be 1. Next is the GPIO per register. It is on page 677 of the datasheet. This register is about to enable or disable weak pulling up resistor. If a bit in this register equals to 0, the corresponding pin has weak pulling up resistor disabled. On the other hand, if a bit in this register equals to 1, the corresponding pin has weak pulling up resistor enabled. In case you forgot what are the weak pulling up resistor and the strong pulling up resistor about, please review them. We have a lesson cover this topic. For this design, we need a weak pull-up resistor enabled, so the pin is sensitive enough to detect if the button is pressed or not. The third register in the list is the GPIO IS register. If a bit in this register is enabled, the corresponding pin can detect voltage levels, which means rising edge or falling edge. Therefore, we need to enable it. Next, GPIO IBE register. Using this pin, it gives us the option to select if we need to use both rising and falling edges. For this lab, we only need a falling edge. Next one is the GPIO IEV register. After configuring a bit on this register, the corresponding pin can detect low voltage level or high voltage level. If the bit equals to 0, falling edge trigger interrupt. On the other hand, if the bit equals to 1, rising edge trigger interrupt. GPIO ICR register used to clear interrupt. After interrupt is handled, we need to clear this bit. Now let's look at the GPIO IM register. Interrupts are enabled or disabled through this GPIO interrupt mask, called the GPIO IM register. If the bit equals to 0, interrupt from the corresponding pin is masked. If the bit equals to 1, the interrupt from corresponding pin is sent to the interrupt controller. Lastly, we need to set the priority of the interrupt, which can be done using the priority register. For this lab, we use PRI7, priority 7, which is the register 36, interrupt 28 through 31. Each PRI register has 3 bits priority fields for interrupt. These registers are byte accessible. Each register has 4 priority fields that are assigned to the interrupts as shown in the table. In the table, bits 31 through 29 for interrupt 4n plus 3. Since n equal to 7, 4n plus 3 is 4 times 7 plus 3 and equals to 31. And from the bottom row of this table, it shows for bits 7 through 5, that is interrupt 4n. Since n is 7, 4n that's 28. So we confirm that register 36, that is for interrupt 28 through 31 priority, PRI7. You can check this information on the datasheet, page 152. I'm pretty sure I did a very good job for confusing you guys, but don't worry, we have another lesson to cover this topic. Now let's begin our code analysis. We start with the main.c file. To use interrupts, we need these 5 functions. You can find the code of these functions in the startup.s file, the assembly source code file. That means we don't have to write any code for these functions. They have been taken care of. Next, declare an unsigned 32-bit integer and let it equal to 0. This variable holds the counter's counting value. It is a global variable, so more than one function can access this variable. Next, declare a function called edgeCounterInitial. We put the interrupt initialization code inside. Follow the steps discussed in previous lesson to initialize interrupt. For this design, we need to use the built-in switch 1 on the launchpad board. Port F pin 4 attached to switch 1. So we need to activate port F. We use syscontrol RCGC GPIO register to activate the port. We set it to be 0x20 to activate port F. Next, initialize the global variable falling edges to be 0. Port F pin 4 connects to switch 1, so it is an input pin. Use port F's direction register to set the pin as input pin. Use AFSCL register to disable the alternative function on PF4. Use the DEN Daniel register to enable the digital feature on this pin. Use PCTL register to unlock PF4. Use AMSCL register to disable analog function. We use the PER register to enable the weak pull-up resistor on PF4. From the PER register map, we can see we need to put a 1 on pin 4. So the code is the register OR equals to 0x10. Next, enable IS register so PF4 is edge sensitive. It is sensitive to clock signals both edges. For this design, our system does not sense both edges. The reason is, when you press the button, the counter increments by 1. But after you release the button, the counter counts 1 more time. So the result is, if you hit the button once, the counter counts twice. So we need to use IBE register to disable the both edge trigger feature. Use AND equal invert operation to clear pin 4 on this register. We use the IEV register to set PF4 as falling edge triggered. Remember that in the IEV register, if you set a bit to be 0, is rising edge triggered. If the bit equals to 1, it is falling edge triggered. Use the ICR register to clear the flag during initialization step. Recall that after the program transits to interrupt service routine, the program needs to acknowledge by setting this flag. Use the IM register to arm the interrupt on PF4. Set the priority equals to 5. Enable interrupt 30 in the NVIC register. At the end, call another predefined function, enable interrupts, to enable interrupt. This is another function available in the startup.s file. Continue. Call a function, GPIO port F handler. This function is the interrupt service routine. Another function that is available in the startup.s file. In this ISR, the first line of code is to send an acknowledgement by setting the flag. It means the program has transited to the ISR, and the ISR tells the system that it's my turn, I'm taking care of it. After setting the acknowledgement flag 4, the global variable falling edges increment by 1. Now let's look at the main function. Call the edge counter initial function first to initialize the port, pin, and also interrupt. Followed by an infinite loop, the while loop. Put the wait for interrupt function inside this loop. This way the program continuously checking if any hardware event is triggered. Also note, this wait for interrupt function is another function that is designed by the original developer, and this function is available in the startup.s